Having taken our first steps away from the pure two-body problem via the introduction of perturbations and orbital maneuvers, we now go even further and explicitly introduce a third body. And as we've said over and over again, as soon as we add a third mass to the two-body system, we lose the ability to completely integrate this system and the ability to write down an analytical solution for the trajectories of the system. However, there is still analysis to be done even in the case of three bodies, and in particular, if we make a few additional assumptions. So rather than studying the full unconstrained three-body problem, instead, what we will look at first is the circular restricted three-body problem, sometimes known as CR3BP. This is an incredibly important problem in the history of astrodynamics and, in fact, modern dynamical systems theory. This was studied extensively by such mathematicians as Henri Poincaré and George Hill and many others. And essentially, the deep study of this specific system gave rise to modern dynamical systems theory and chaos theory. The setup of the circular restricted three-body problem is as follows. We have two primary masses, which we will call M1, M2, and we have our orbiting mass, M sub p, which is much, much smaller than the two primary masses. We will assume that the orbiting mass, the test particle or spacecraft or whatever, is so small compared to these primary masses M1 and M2 that it has no effect on their orbits. We will further assume that M1 and M2 are on mutually circular orbits. O here is the barycenter of M1 and M2, and we will introduce a new parameter, mu star, that is equal to the mass of the smaller of the two bodies, which by convention we will set to M2. We will be operating in a non-inertial rotating frame that is effectively equivalent to the Euler-Hill frame that we previously introduced, with the first unit direction, E hat r, being along the direction of the radial line pointing from M1 to M2. M2, you will recall, is in a circular orbit, as is M1, and so this E hat r direction has the exact same definition as in the Euler-Hill frame. E hat theta will be orthogonal to E hat r in the plane of the orbital motion of the two primaries. And we finally have a third direction, E hat z, which is in the direction of the angular momentum of the orbit of the two primaries. The test particle, the mass that we care about in this system, is not constrained to the plane of the orbit of the two primaries, although in the restricted form of the three-body problem, we only consider the particle's motion in this plane. We will shortly see that just as in the Euler-Hill or Cohesi-Wiltshire equations, the out-of-plane component of the particle's motion effectively decouples from its in-plane motion. We're going to be operating in a set of canonical units specifically designed to non-dimensionalize the problem. We will pick a time unit, TU, such that 1 TU is equal to the orbital period of the primaries divided by 2 pi. This means that the mean motion, the angular velocity of M1 and M2, is going to be equal to 1 in this system. We will pick a distance unit such that 1 distance unit is equal to the orbital radius of the first primary with respect to the second primary, or equivalently the second primary with respect to the first primary. And we will pick a mass unit such that 1 mass unit is equal to the sum of the primary masses. So putting all of this together, you will recall that the gravitational parameter for the primaries, gm1 plus m2, is equal to their mean motion squared times the semi-major axis of their orbits cubed. N is 1, A is equal to this radius is 1, the mass unit is 1, and therefore in this system of units, the gravitational constant is exactly 1. So in this unit set, since we have defined the mass M2 as being this mu star parameter, the mass of M1 must be 1 minus mu star. And by the center of mass equation, in the distance units that we've defined, that means that the more massive primary, M1, must be a distance mu star from the barycenter, and the less massive mass, M2, must be a distance 1 minus mu star from the barycenter. And so we can write the position of mass 1 with respect to the barycenter, the more massive mass, is negative mu star E hat r, it is in the negative E hat R direction from the barycenter by convention, and the position of the less massive mass, M2, with respect to the barycenter, is given by 1 minus mu star in the positive E hat R direction. So what do we do with this setup? Well, as usual, we apply Newton's second law. And so the force on the particle is now the force due to its interaction with both the primary masses. This first term represents the gravitational force on the particle due to the primary M1, and the second term is the force on the particle due to its gravitational interaction with mass M2. We are operating in this rotating frame B, whose angular velocity in the inertial frame is given by the mean motion of the primaries in the E hat 3 direction, the out of plane direction, and we've already defined a unit set such that n is equal to 1, so I omega b in this case is just E hat 3. We've already gone through the exercise of applying the transport equation twice to a position vector and figuring out the relationship between an inertial acceleration and a rotating frame acceleration. And this is exactly the same result that we got for the Cohesi-Wiltshire equations, except in this case, the mean motion is strictly 1, and the force term on the right-hand side is now given by these two forces. We will once again, exactly as with the Cohesi-Wiltshire equations, be operating in rotating frame Cartesian coordinates. We will describe the position of the test particle or spacecraft with respect to the barycenter of the two primary masses in rotating frame components using coordinates x, y, and z. Finally, we will define r1 and r2 as the magnitudes of the position vector of the particle with respect to the masses m1 and m2 respectively, and we can write these as functions of our coordinates and this mu star parameter only. And the only thing operating in the system is gravity, which is a conservative force. And so we must be able to write this force as negative the gradient of a scalar potential. And if you crunch through the math of this, you will find that this V term has to have this form. So we plug these components into the left-hand side of this expression, and we get these three equations. And then on the right-hand side of this expression, we have negative the gradient of the potential as follows. What we're going to do next is analogous to what we did when we first studied specific energy and defined an effective potential term that grouped together the actual potential energy of the system, along with all terms in the relevant equations that were functions of position coordinates only, and isolated everything that was a function of the derivative of position, so velocity-like terms. So in this case, that means that we're going to grab our potential function v, and we're also going to grab the parts of these things that are purely functions of x and y. And that allows us to define a new potential, which we will call u, which is the original potential v, and everything that is a function of x and y. With this definition of u, our equations of motion for the rotating frame components of the orbital radius vector of p, our test particle with respect to the barycenter of the two primary masses, takes this form. There's a really important observation to be made from these equations. If we look at the expression, that is, we can write x double dot times x dot plus y double dot times y dot plus z double dot times z dot, and then replace each of these second derivatives with these equations here. Then we will get negative partial u with respect to x times x dot plus 2x dot y dot minus partial u with respect to y times y dot minus 2x dot y dot, canceling this previous term, and finally minus partial u with respect to z dot. This is exactly equivalent to 1/2 of the total derivative with respect to time of x dot squared plus y dot squared plus z dot squared. And this is exactly equivalent to the total derivative of u, our new modified potential, with respect to time, which is the observation given here. What can we do with this? Well, note that this is a representation of the body frame velocity of p with respect to o norm squared. We have two exact differentials on either side of the expression with respect to the same variable time. And so we can integrate these. And when we do so, we get the Jacobi constant. So this is exactly the integral of the preceding equation. and we set it equal to a constant of integration, which we will call capital C, which is the Jacobi constant. We apply the transport equation in reverse and write that the body frame velocity of P with respect to O is equal to the inertial velocity of P with respect to O minus the angular velocity of B and I, which in this case is just E hat 3, crossed with the position vector. Plugging that into this expression, we get 1/2 the inertial velocity dotted into itself, which is the specific kinetic energy of the system, plus the original potential term. So this is our original V. And so altogether, this is the specific energy of our test particle. And then everything that remains is the inertial velocity dotted into E3 crossed with our PRL O, which you can verify because we've split up our potential into its original constituent parts. We can circularly permute this dot cross product to find that this is the same as E3 dotted into R cross V, which of course is the specific angular momentum of our test particle. And that means that in scalar terms, this equation is the specific energy of our mass P minus the specific angular momentum of our mass P projected into the orbital plane of the two primaries. And if we define the inclination, I in this case, as the angle between the current orbit of P and the E1, E2 plane, the orbital plane of the two primaries, then this entire expression can be written as H cosine I. And these two terms together must equal our Jacobi constant, which is entirely set by the initial conditions of our test particle's motion. So taking a step back, what is it that we found here? Well, we do not have, as in the two-body system, independent conservation of the energy or of the angular momentum. However, energy and angular momentum must be jointly conserved via this relationship. So there's going to be a trade-off between the orientation of the particle's orbit, its angular momentum magnitude, and the magnitude of its specific energy. And via this relationship, these three terms must maintain this constant value. The only way to get away from this constant value is to add energy to the particle. So if the particle represents a spacecraft, you can change the C value by applying Burns. The other thing to note here is that because this quantity is strictly positive, we have 1/2 of the norm squared of velocity, C in our definition is strictly defined as being greater than or equal to this modified potential U. The only case in which they're equal is at the point when the particle has 0 velocity in the rotating frame. In many other texts, you will also find C defined as negative, the value that we've defined it here, or some scalar multiple of negative the value, such as -2 of the C that we have here. Because it's a constant, it really doesn't matter. There's just different conventions. We will use this one, but don't be surprised if in your reading you encounter other conventions where the sign flips. This idea that C is bounded by U, such that C is always greater than or equal to U, means that contours of the rotating frame potential, U, are 0 velocity curves of this system. Curves of constant values of U represent effectively barriers in space in the rotating frame. An object with a specific C value cannot cross the relevant contour of the U equivalent to that C value. The contours of U are frequently known as the Hill curves, and they are parameterized by mu star only. So given a value of mu star, we can plot the contours of that three-body system. And so here's an example for mu star equal to 0.3. You will recall that this means that the smaller of the two masses has a mass of 0.3, and the larger of the two primary masses has a mass of 0.7. And in this plot, the colors represent the magnitude of the contour. This is the location of M1. This is the location of M2. And you will see that effectively you can have orbits around M1 because, again, in the rotating frame, these represent barriers that a specific test particle with a specific value of C cannot cross. So if you are at the effective C value that corresponds to this contour and you start your life here, then you will always remain in this vicinity, orbiting M1. Similarly, if you have that same value and you start around here, you will spend all of your life in a trajectory about M2. Alternatively, if you have approximately that same C value, but you start all the way out here, then you will effectively be orbiting both of the masses. And the idea here is that as distance goes to infinity, these two masses, M1 and M2, the distance between them becomes much, much smaller than the radius of the test particle's orbit. And so they effectively become a single mass that you can orbit around. This is something that actually happens. We now know of planets orbiting binary stars, not orbiting one of the two binary companions, but actually orbiting both of them together. And then there's interesting things that happen in between, where if you have larger values of C, you can do interesting stuff like cross between different families of orbits, or even be in some vicinities of space where there's no mass. And we're going to get back to that idea very shortly. The last thing that we can say is something about the symmetry of the system. It is completely symmetric about the radial direction. So everything above the radial line, the vector from M1 to M2, looks exactly the same as everything below, but it is not symmetric about the orthogonal direction, the E theta direction. And that is because these masses are allowed to have different magnitudes. If we had exactly equal masses, if M1 and M2 were exactly equal and mu star was 0.5, then that is the only case where we would have symmetry in both dimensions. This is just a three-dimensional rendering of that exact same contour plot. This is on a logarithmic scale, and so it's plunging down to negative infinity here around M1 and here around M2. And you get this idea that there are bridges between them and bridges to the outside world. And this is another concept that we will return to. If we just look at the mathematical structure of our rotating frame potential U, in the limit as x and y go into infinity, U has just the form of negative x squared plus y squared over 2. That our whole original potential drops out. And that is exactly the statement that we previously made, that as your test particle gets infinitely far from your two primary bodies, it behaves as if the bodies are just a single mass. If you go in the limit where y is 0, where the E theta component is 0 and you're on the radial line between the two bodies, and as x, the ER component, approaches negative mu star, then the potential behaves as if you're only affected by the first body. And similarly, if you go to the location of the second body, then the potential behaves as if you're only affected by the second body. So you can be in orbit around the first body, perturbed by the second body. You can be in orbit around the second body, perturbed by the first body. You can be in orbit around both of them together, or you can be doing something else. And that something else is where all the really interesting stuff happens. One final view of this exact same thing, we can animate stepping through the various slices. And this again kind of gives us this idea of either orbiting one or the other body, or maybe at a certain point, if your energy is high enough, crossing between them or crossing out into the outside world of the system.